Today, I'm pleased to introduce Carolina Camargo, who's coming to us from Woods Hole. It's going to be talking about the Shelfbreak front. She got her BS in Oceanography from the National University, or the Federal University of Rio Grande in Brazil, and then a MS in Marine and I'm not going to be able to say this again. What's it called? Street.
I mean, you're the English one.
Yeah, it's lakes, but science management in Belgium, and then a PhD in geosciences from Delft University. And since
where? I'm sorry.
Delft.
Oh, Delft.
And since 2023, she's been at HUI working with Chris Baikuch and Britt Rabenheimer on coastal sea level. And she's done a bunch of other stuff. She's been working with SWAT. She's been doing some machine learning stuff. She's done some outreach. You have a paper in Frontiers of Young Learning, I think. Yeah. So very varied. But I'm very interested to see what you're going to tell me about coastal sea level. Take it away, please.
But yes, I'm Carolina. Thank you for having me here. As Christopher said, I'm a postdoc at Woods Hole currently. And today I would like to present some of my postdoc work, which is looking at the Shelfbreak jet current and how that is connected with coastal sea level in the Mid-Atlantic Bight. So I like to start with the picture in the background, where you can see very large wave reaching the coastal. Yeah, so I like to start motivating what I do basically with this photo in the background, where you can see very high waves reaching the waterfront street in Woods Hole Village. And I also like that there is NOAA in the back, which I find a bit ironic, how we have very high waves coming to the water and all the science buildings around it. But that just goes to show, right, that this was not always an issue. Of course, when they built the NOAA fisheries there and all the Woods Hole, HUI and everything, this was not happening that frequently. So this just motivates us. We have to know why sea level, why this is happening. This is, of course, the effect of a storm, but storms have been happening for a long time, and this wouldn't happen always. So it's your background signal that is rising, and what is other things that are causing it. So Christopher already introduced me, but I still have some slides just introducing myself. I'm from Brazil, from close to São Paulo, and I went to the very south of Brazil, so almost to Uruguay, to get my bachelor's in oceanography. So I studied all the parts of oceanography, but I consider myself more physical because that's where I went into deep a little bit. But I've always been doing some sort of sea level research. So for my so for my bachelor thesis, I was working with paleo sea level, so looking at evidences of coastlines when on the last glacial age, when the whole the whole continental shelf was exposed. So using geophysical records of to see how finding like old paleo channels and old coastlines. I then went to Belgium for my master's, which has this marine and lacustrine science and management, which we just shorten it for oceans and lakes. And for my master thesis, I was working with real-time sea level data from tide gauges worldwide, and looking at the quality control of that, so a bit more technical. And then I went to TU Delft and NIOS in the Netherlands for my PhD. And for that, I was looking at what drives present-day sea level. And by present day, I mean the last 30 years. But I'll talk a little bit more about that. And now for my postdoc, I'm here at Woods Hole, looking at coastal sea level. And in that little map, I have pointed where I've been. So not only in Belgium and the Netherlands, but I've also been to other places doing some research in Portugal and Spain and Canada, and happy to talk about experiencing a little bit the international setting. So again, another motivation slide, like why we care about sea level. And I really like this cartoon. It's very dramatic. This is not gonna happen. We are not gonna be with the water almost at the trees, but yeah, it is rising and it's gonna impact our lives everywhere. And here we have the projections from the latest IPCC report, showing that global mean sea level will likely rise between 1 to 1.7 meters in about 100 years. But that's for the global mean. And probably everyone here is aware that sea level is not the same everywhere. So here we have the global mean curve of sea level over the last 30 years. So during the altimetry period on the right corner, and we have a map for the same period of the trend, and the colors are diverging around the global mean trend. So if it was all the same, everything would be this a very pale color, but you can see that everything that is a little bit red is higher than the global mean, everything that is a little bit blue is lower than the global mean. And that's because what causes sea level to change, all these different drivers have their own spatial temporal signature, and it's going to affect sea level differently in different locations. So what causes regional sea level change? Well, this is not a cause, but this is just how we observe the total sea level change by either using satellite altimetries or by using tide gauges. So instruments really located at the coast, measuring point-wise, and you have these altimeters that are going around the globe, measuring sea level. Different than with a tide gauge, you get measurements depending on the gauge, but about every minute, every hour at least, you're going to have a measurement. Satellite altimeters are going to repeat depending on the mission, about every 10 days. But you get a global picture, including the open ocean. But that is the total sea level change. We have also, you have the different drivers of sea level. So you have how much sea level is changing due to steric expansion of the ocean. So because we are varying the temperature and the salinity of the oceans, and this is going to cause your density to change and expand or contract, depending on how temperature and salinity are varying. You also have sea level change due to dynamic components, so due to the effect of ocean currents and winds. And usually these two components are studied together, called stereodynamic, because also we cannot really isolate temperature from ocean currents and so on. And you have how much sea level changes due to mass changes, so by literally adding more mass into the oceans, by melt from glaciers and ice sheets, and by varying the amount of terrestrial water storage. So basically, we can break down sea level into these different components. You can include one or other different components depending on the time scale that you are looking at. So for my PhD, I was looking at these different components, and I focused first on the steric component and on the mass component. And I'm just showing here the studies. Not going to talk about this today, but happy to chat more about that. And then, this whole system is what we call the sea level budget. And that was my goal, was to look at the sea level budget on a regional scale. And for that, I had to use some machine learning techniques to find these regions of coherent sea level so that we can better explain regional sea level. And again, I'm not going to talk about this, but just some self-promoting here. But what I got from my studies is that the dynamic part of this little scheme was the part that we had most uncertainties on. So I was using ocean reanalysis to look at the dynamic component, but it was a bit circular because they have altimetry and so on. So I was a bit more curious about exactly how ocean currents and sea level are related. And that was what drove me into my postdoc work, which was then having a study case of how coastal sea level and local ocean dynamics are related along the US Northeast coast. And there was a reason why I chose that, why I chose this region. So first, I mean, of course, it's a very well studied region. It's very oceanographically interesting. We have the Gulf Stream, of course, very strongly, that it attaches from Cape Hatteras and starts flowing towards, towards Europe. And I mean, considering we are in Stony Brook, we are all aware, I guess, of the Mid-Atlantic Bight. In case anywhere you don't know, you have a global map there in the top. But we have also this slope sea gyre, so this recirculation gyre that forms north of the Gulf Stream with a slope sea current related to this. And we have also the Shelfbreak jet. So the Shelfbreak jet is a current that is flowing north from the Labrador Sea down to Cape Hatteras following the Shelfbreak. And it's 2 orders of magnitude smaller than the Gulf Stream. But as we will see, it's actually quite important for sea level in this region. And yeah, so the reason also why I chose this is if we want to quantify the relationship between sea level and ocean dynamics, we need good observations or a good model, but in this case, observations. And yeah, the Mid-Atlantic Bight is perfect for this. So here we have, so all of these circles are indicating tide gauges along the coast, which I find already a very good coverage. Some people still think it's not enough, but compared to other coastlines is already very good. But more specifically, we had the Pioneer Array. So these are indicated with the triangles there, which was an array from the Ocean Observatory's initiative, an array composed of 7 moorings that was there for about 7 years, so from 2014 until 2022. So this gives us like the basic ingredients that we needed to look into this relationship. So the objective of today's talk is to, well, talk about the relationship between coastal sea level and the Shelfbreak jet. But the talk is broken up into 2 parts. So first, I want to talk a little bit about the Shelfbreak jet in case people are not familiar with it. I think that, yeah, a lot of the research here, a lot of research is being done by people from here on the Shelfbreak jet. So probably you are a bit more familiar, but I still would like to go through how the data from the Pioneer is for the Shelfbreak jet, and then we're going to focus on sea level and the Shelfbreak jet. And these are the questions that we're going to go through. So what are the climatological velocity values we find with the Pioneer? Is the Shelfbreak jet always there? And then what is the relationship? And also I've been looking a little bit into if there are any floods related with this Shelfbreak jet and sea level relationship. So starting by part 1, obviously. Again, here we have the Pioneer Array. I highlighted around this with a circle. So it's located just south of Martha's Vineyard along the Shelfbreak. And here we have a zoom in. So I think you can see. So you have the 7 moorings, 2, they are inshore on shelf water around 90 meters depth. You have the 3 central moorings in the jet region, and that goes from about 130 to 150 meters isobaths, and you have 2 offshore moorings in the slope water, about 450 meters depth. And yeah, so we had measured, so the Pioneer was there from 2014 until 2022. And the moorings, well, some of them had a surface, depending on them, you had 2 types of moorings, but in any case, you had a bottom mountain ADCP. So the ADCP is close to the bottom, looking up, giving us velocity. oh, sorry, did I blind someone? No. I am not very good at this, but so we have our ADCP either mounted on this multifunctional node, really in the bottom, or on the rope, but still close to the bottom. Again, it's looking up, giving us velocity through the whole water column. But yeah, point-based, right? Of course, they are fixed. And just to give, yeah. So, I mean, our ADCP is gonna measure the eastward and the northward components of velocity. So considering where the coast is, so I drew this beautiful coastline there. Where is it again? I lost it. Anyway, you can see it there. And you assume that the Shelfbreak jet is crossing through the jet region. So east is towards the left. No, sorry. Yeah, east is towards the right, and west is towards the left. So when we have our jet is flowing towards the west, so negative velocities mean that we actually have the Shelfbreak jet. Positive velocities means that, well, the Shelfbreak jet is being interrupted. We also have our northward velocity, which would be the cross-shore component in this case, but I am not gonna go into the cross-shore component at all today. Right, we have hourly data and some basic quality control. I removed any data that has been flagged as bad, removed the top 15% of the water column due to interferences with the atmosphere, with the ocean interface. Also applied a global range to remove outliers and removed barotropic tides. So this is a little bit how they look like. And I'll admit this is not the best way of plotting our profiles because some of them are aligned. So you're only seeing 5 lines, but there actually should be 7. But the inshore ones and the offshore ones are really well aligned. So I should still think of a better way of plotting this. But what we have here, right? So here we have our annual mean. And here you should have your two moorings. And here, the offshore one. And here is the monthly. So we can see that the offshore ones, and in this case, red is negative velocities. So that means westward flows, and blue is eastward flows. So you see that the offshore moorings, they change the direction quite a lot, and that this is expected. This region is more influenced by rings. Yeah, I'm not sure exactly how. You would still expect your slope gyre there, but I think that any of these inversions are related with rings in the offshore ones. And we can see the jet strongly, its surface intensified. And you can see that it gets stronger through the winter months, like late fall and winter. And this is to show the maximum velocities for the monthly means and for the annual. And so these are for your inshore moorings. The 2 bottom ones are the slope moorings, and the 3 ones are our central, so our jet moorings. And we can see very clearly that from November until December, it's very dark, meaning that we have very strong velocities, reaching almost 0.2 meters per second. And the offshore ones, they don't have such strong ones. And during the summer is when we have weaker jet. And yeah, again, not the best plot, but this is to demonstrate in which depth we are looking at. So in the previous one, I had the maximum velocities. And here is the depth for each of those velocities. But basically, we see we find our velocities mainly towards between the first 15 to 20 meters. In the offshore ones, it's deeper. And during the summer months, we also find deeper pore velocities. So this is the time series actually of each of the moorings. And from here onwards, I have averaged the moorings, so the 3 jet regions and the slope ones and the shelf ones, and that's to improve the time coverage of them. And assuming they are aligned, the 3 central ones are not aligned, but we assume that any cross shelf transport between them is very small, so that you can basically treat it as one. Big assumptions, but we go for there. And this is how the time series depth integrated look like. We have on the top for the shelf, in the middle for the jet, and in the bottom for the slope. So the bigger points are weekly averaged, and the small little dots in the back are hourly. And here, everything blue is going towards the west, and red is towards the east. And I want to get your attention to the jet series. So this is for those 3 central moorings averaged. We do have it as we expect, that the velocities are mainly towards the east, towards the west, but you do have some reversals happening, which are here in red, and some even long ones that can last here. I think you have 3 weeks. So what exactly happened there, I am not 100% sure. It can be because we have moorings that the jet is just going more inshore or offshore, or it can also be that we had rings intruding all the way into the shelf. So things still to look into. Yeah, and following the same line, so trying to answer if we can always identify the Shelfbreak jet. So there was a study from a PhD at Hui a couple of years ago that looked at the oleander line. So basically a little bit of a follow-on on some studies from the group here also. And they said in that work in 2020 that based on the oleander line, they could see that the Shelfbreak jet is intermittent in both space and time on the New Jersey bight. So I tried to, using similar parameters to what Foresight had used, I tried to see if we could always identify the Shelfbreak jet based on my time series. So I maxed out any of the times that, so he had 4 criteriums, and I maxed out things that wouldn't fix the criteriums, and we would say that actually there you have some times here that we would not identify the Shelfbreak jet at all. So that would be about 56%. I have here ours, but it's actually weeks that we can say that we can strongly observe the jet, and about 50% not. And again, why that is up to discussion. So just to summarize this first part, we see that we have, and so the Shelfbreak jet has annual values of on average of 0.12 meters per second at about 17 meters depth. The jet is maximum from late fall to winter, so from November to February, with velocities of almost 0.2 meters per second, also between 10 to 17 meters depth, and it's weaker in the summer.
Excuse me, those units, we've got meters squared per second.
Yeah, the bottom one here is depth integrated. These are not depth integrated.
So it's really the transport per unit depth.
Yeah, in the bottom one.
Yeah.
Width across the shelf. Is that average for all the moorings, or is it one mooring?
Where, sorry?
That graph.
Yeah. this is these three central moorings. Depth I averaged them first, and then I depth integrated it. So would be the transport of the jet. And relate.
So it's 3 more.
Yeah. Yeah. So in terms of if the jet is always there or not, we see that we have some reversals, mainly on a daily time scale, but sometimes it can last up to a few weeks. And following the parameters from previous works, we can identify about 56% of the week from 2018 to 2022, actually. So all of these numbers are focusing on the period where we had stronger overlap.
So what are those timescales of variability? They're synoptic period or the reversals, roughly?
Yeah, I think mainly synoptic.
Well, there was a big event about January 2020, see where it changes direction abruptly.
Yeah. I didn't look so much in depth into what that was. I do think it's related with a year that we had a lot of rings, but I don't know if that is the occasion. Yeah, but these are some of the follow-up questions that are coming into now, like, yeah, what happened there and why did that happen? Yeah, so I think looking at some temperature and salinity also might give us some answers there. So now that we know how the Shelfbreak jet looks like, then I move to the main question actually that I had, that is, what's the relationship between the Shelfbreak jet and sea level at the coast? And then a follow-up question that is, if any, are there any flows related to this? So again, here just we have all this. We have all of our tide gauges located through the coast and the Pioneer there. And to answer this question, I'm gonna explore it via some coherence and some admittance analysis. So just to freshen up, you can think of coherence as a correlation in function of frequency. So it's gonna tell us how these two signals are correlated as we move to frequency. And admittance, you can think of that as a regression in function of frequency. So it's gonna tell how much changes into one unit is sensitive to changes in another. And just as correlation, coherence has no units. I lost this again. Anyway, but admittance has units. So depending who is your input and your output, in this case, we have admittance in units of meters per units of sea level per transport. So meters per square road. And we are first going to focus on sea level average through the southern New England, so average through those tide gauges that are highlighted in the circle. So these are how the time series look like. We have in blue sea level average over southern New England, and this is plotted in relation to the left y-axis, and we have a long shelf jet transport plotted in relation to the right y-axis in yellow. And we can already, just by looking at it, we can see that there are some periods that are a good correlation and some periods that they do not seem that much in phase. And I also would like to call the attention to the fact that the y-axis of transport is flipped. And that was because first I had them both in the same direction, and when I flipped it, you could see better the correlation. So just for terms of visualization, and our coherence analysis does show that they are always at 180 degrees.
I'm sorry,
phase.
the brown is the transport.
Yeah, yeah.
And the blue is sea level.
Yeah.
So if you look at the halfway between 2015 and 2016, the brown line goes a big dip down, but has no effect on sea level.
Yeah.
So is there a correlation or?
Well, so for that case, the correlation is very, very weak. And yeah, I think one of
See
the,
that quite a bit, you go along like halfway between 21 and 22,
yeah,
same thing, brown line is lower by
yeah,
quite a bit.
yeah. So, yeah, not sure what is happening there. But you do have other periods then where they seem to be matching very well. So I guess I was looking just at the whole thing and trying to see what can we get out of this, but maybe I guess, yeah, some follow-up analysis might be looking at individual events, like what happened in late 2015, what was happening, I don't know. If you know, I would be love to hear. Yeah, and this is just a zoom in a little bit of 90 days. And so the zoom in period is highlighted here with the dashed lines. And let's be fair, I chose a good period to show here, but we can see very well how these two signals for certain periods, yeah, you have a very good match of one going down and the other going up. So it seemed even too good to be true. But it's of course not always the case. If I would be showing here, maybe I should have an also plot showing that. You would see that's very deep. So this is how the coherence looks like. So we have here the x-axis is, keep losing this. Anyway, the x-axis is periods. So we have, say, 0 on the left, up to 15 days on the right. And I have some vertical dashed lines just to indicate where we are on the period line, just so you know, 1 and 2 and 4 days, just to have an idea. And we see that basically from 1 day onwards, we have a coherence that is higher than 0.3. So we consider that by that we start having a significant coherence. This is stopping at 15 days because doing spectral analysis, you have to choose how many segments you have. And so basically, if we would go towards lower periods, we were getting too noisy and could not solve things anymore. So I'm stopping at 15 days. So some processing choices when you're entering the spectral realm.
There's a case.
And this is how the admittance looks like for, yeah, so that is plotted in relation to the right y-axis. And I've masked out any admittance when we have low coherence, because we should not interpret an admittance if our coherence is about 0. So you do have these high values here, but your coherence is very low. So we should try to not look at that. So we see that for when we have a high coherence, we have an admittance of about 0.25 to 0.3 meters per square group. And just to give a ballpark of how does this look like, if we look at it with relation to the AMOC transport, the sensitivity of sea level to that is about 2 centimeters per square group. And we are finding 30 centimeters per square group with the Shelfbreak jet. So this gives an idea of how important this current actually is for our region. Right, but so we were bounded there for the 15 days due to the choices of the coherence and of the admittance. But we can look at the wavelet to look towards lower periods. So basically our coherence before was stopping around here. Cannot make a straight line, but about here. And now we can get up to 2 years. And we do see, like this, it appears, so high colors are high coherences. And the same with the admittance here, dark colors are higher admittances. And we see these blobs that appear between 20 to 40 days that are quite intermittent. And I think that, yeah, somehow, I mean, this is saying that it's highly coherent on this time period. And it also goes where that time series was going low. I'm not sure how to interpret that, to be honest. But what we see is that our coherence is very intermittent, right? We have very striking bands of low and high coherence. And this is accompanied, followed, comes together with high and low admittance bands. And that's why basically when you average this through time, you get the time series that it's not quite like what we were looking at before. And this is all looking at the average time series of these tide gauges here. So we can expand a little bit the spatial domain saying by then looking at the individual tide gauges. So I did the same coherence and admittance for the Shelfbreak jet with each of the tide gauges. And this is what is plotted here. We have here our tide gauges from north to south. And here is the mean coherence in red and the mean admittance in green for those different bands that we had. So between 1 to 2 days, 2 to 4 days, and 4 to 15 days. And the admittance for the same thing. And what our map is showing is the peak coherence. So the color is when we reach the peak. So all of the time series had a peak of coherence, and then it kind of slopes back, and it stabilizes, kind of. So what the colors are showing is when this peak happens, and the size of the circle is the number of it. So, for example, we have all of these tide gauges here. They have about between 1 to 2 days, we reach that peak of about 0.3 coherent. And as we go further to the south, this coherence happens later on our period. So up to close to 14 days, and it gets even smaller as you go. And the peak is much lower when we go south of Cape Hatteras. And what we see, we see the same thing by looking at the average values here. So we see, the time series here from Woods Hole, so the tide gauge from Woods Hole to Kings Point, they show these high coherences between 1 to 2 days. And as we go towards 2 to 4 days and 4 to 15 days, the area of high coherence and high admittance expands more towards north and south. So between 2 to 4 days, we are starting to reach, Outer Cape and all the way to Atlantic City, say. And then as we go between 4 to 15 days, you have high coherences all the way up to Maine and all the way to Duck in North Carolina. And they are always followed by admittances, varying between 0.2 to 0.4 meters per square dome. So this is all very just statistical relationships. I didn't look into the dynamics more than that.
But you're assuming with the admittance, there's some geostrophic relationship.
Yeah, we are assuming a geostrophic relationship between the jet and sea level.
Just my comment, if you look at, like, it peaks up around about Montauk, New London, Montauk, that's eastern Long Island Sound, and you have the discharge of Connecticut River, Housatonic River. They're the only significant rivers until you get down to Chesapeake Bay. So just wondering, that discharge of those rivers can affect sea levels independent of what your study.
Yeah, but then you wouldn't expect to find a coherence. So what this is saying is just what is the relationship of sea level with the Shelfbreak jet, but it's not saying that that is explaining the total variation of what is happening at the tide gauges. So you'll have a lot of the influences of the rivers, you'll have a lot of wind influence, and yeah, so this is not saying that this is the only thing, but it's one thing.
Quick question. If you look at your sketch in the upper right,
Yeah,
do you assume the relationship gets stronger as you go further to the southwest, where the jet is closer to the coast, or no?
I mean,
You don't see it immediately?
you don't see it.
Okay.
And
That's, you're looking at the Pioneer array
Yeah,
Exactly.
sorry.
versus Chesapeake, and they're
Yeah.
a long ways apart.
Yeah, sorry.
Yeah.
This is Pioneer data.
yeah, so exactly. So I think that a lot of why we don't see a high value when the Shelfbreak jet is actually closer to the coast can be due to the fact that we are using data at the Pioneer.
Got it.
Would be super nice to have actually transects going following the shelf. Don't think that that's exists. Yeah, so what we like, yeah, so basically what all of this told us, and when we look at again this time series, we see this very high coherence relationship between 1 to 15 days. With a high sensitivity of sea level to changes in the transport. So that led us, when you think about 1 to 15 days, this matches a bit when you're thinking about the time series, the frequency of storms. So led us to the question, well, are actually any flood events registered in this region that are related with the Shelfbreak jet-driven variability? So this is ongoing work. So to answer that question, okay, so here we have any flood day, any events where sea level was higher than a flood threshold for the Nantucket tide gauge from 2014 until 2022. So we had 33 days of flood. So I got the maximum value at each of the tide gauge. We have these flood thresholds defined by the National Weather Service, which is indicated here with the dashed line. And the bars are indicating the height at the tide gauge, the raw height at the gauge. So you see some very strong events. Well, you see some very strong events right in the beginning, January of 2015. You also had the very big storm in 2018, in March of 2018. So to see if the Shelfbreak jet was adding to any of these floods, what I did is so I band past the time series between 1 to 15 days, because that's where we found that they are coherent. And you can do a linear regression between them and reconstruct sea level based only on the tide, on the Shelfbreak jet transport. And then you can remove that from the tide gauge. And that is what this other time series would look like, the peaks for those days. So in orange, then you have what would be, say, sea level at the tide gauge minus sea level due to reconstructed with the Pioneer. And you see that the bars are different than the blue bars. And especially I want to highlight that we have cases where it's much lower than it actually was. So for example, here and here, so by following that this is our flood threshold, we would think that in these cases, if we remove the variability due to the Shelfbreak jet, we would not have a flood. So that is what's highlighted here. So these are events that the Shelfbreak jet contributed to the flood. So floods that happened that would not happen if we didn't have the Shelfbreak jet. And by no means is the Shelfbreak jet is the main factor, but it can be sometimes the less drop on the water glass. So that was for Nantucket. So again, given that a flood happened, what is the probability that it would not happen without the Shelfbreak jet? And this is what this map is telling us. So the probability of a flood that happened not happening without the Shelfbreak jet. And we see that it's usually about 30%. So for the case of Nantucket, those I know the numbers by heart, we had 33 days of flood, 10 days of flood wouldn't happen. So that's about 30%. So I'm starting to look at the wind, because of course those are very important for when we have a flood. So following the same line, I regress off the wind from the Shelfbreak jet and redo this part. And we get these new orange bars where this is sea level without the non-wind part of the Shelfbreak jet. And yeah, I was just doing this really a couple of days ago, so very fresh. But we see it's not now, before we had 10 days that was below the threshold, now it's only about 5 days that is below the threshold. So that would be, yeah, cases in whatever the non-wind variability of the Shelfbreak jet is added. So it's less than what we had seen before.
When you talk about wind, the wind is a vector, right? It's a speed and direction. So
I use
storm surges are often related to onshore winds.
Yeah.
But so what do you mean by wind?
So I'm doing a multiple linear regression here using both the northward and the eastward wind. So both components to make sure that we are capturing that, because it will depend. So especially when we are looking in Nantucket, the tide gauge is, so most of the tide gauges are, you will have wind blowing there. If you have very strong wind, you have a surge. But with the Nantucket, where it's on the other position of the
Right, and then you have the effect of ectonic turning. So it's like
Yeah.
South Shore Long Island.
Yeah.
You might get maximum sea level fluctuations with winds parallel to the coast, not pointing straight at the coast. So
Yeah.
it's complicated. It varies where you are.
Also, Nantucket is an odd man out in the sense that it's at a knuckle in the coastline.
Yeah, exactly.
As compared to Long Island or New Jersey or someplace like that.
So the reason why I started with Nantucket was because it has, the tide gauge has also a record of wind. And it's the most complete one. So some other tide gauges, I think the one in Montauk also has winds, but it's a bit gappier. So that's why I started with Nantucket. So this is also using the wind from the tide gauge, and now been using it. I'm looking at Era 5 wind and looking at wind at the Shelfbreak jet position, and also some remote wind more north. So
Winds tend to have 500 kilometer sort of scale.
Yeah.
So you might include a large scale average to look at the impact.
yeah, so I'm looking at this now. Yeah, so just to summarize this last part, so we had the question, what's the relationship between local ocean dynamics, and by that I mean the Shelfbreak jet and coastal sea level. So we see that they are significant coherent between 1 to 15 days, and the spatial extent of this coherence increases when we go towards lower frequencies. And we find an admittance of 0.3 to 0.4 meters per square group, depending on where you are and the frequency. By using the 1 to 15 days band, we can reconstruct about 40% of the variability of each time series. What I didn't show, but I briefly mentioned, is that the coherence and the admittance indicate what we already could see by just looking at the time series, is that the jet and the transport are out of phase. So you have a phase of about 180 degrees, which makes sense that as the jet's becoming more negative, so as it's intensifying, you have sea level positive and the other way around. So consistent with a geostrophic assumption. And the second question, if any floods related to this relationship, we see that without the Shelfbreak jet, the number and also the timing of floods change. And it's conditional. So what I was showing is that we had days that it removed. We also have some days that it adds. But yeah, again, this is everything very still fresh. But about 30% of the flood that happened would not happen without the Shelfbreak jet. And now I'm looking into other storm atmospheric variables. So I'm looking at wind, and I'm looking at pressure and waves to see if we can explain a little bit better. And also, yeah, what is causing this variability in the Shelfbreak jet? That's the next question. Say question 1 of part 2 has been published recently. So in case anyone wants to look a little bit more in details in that. Yeah, that's it.
We have time for just a few questions,
Yes,
but
sure.
before we do questions, I wanted to remind everyone that there's going to be lunch in the Swenson room after this. And then graduate students will have an opportunity to chat with the speaker at 1:45. And she'll be around until about 3 if anyone else wants to chat with her. I think Malcolm didn't get a chance. Does anyone have any questions?
I got a couple of comments. I'm surprised a bit at the seasonality of the transport of the jet. There's an enormous difference between the hydrography in the wintertime and in the summer. In the winter, the Shelfbreak jet is sort of horizontally confined. But in the summer, the Shelfbreak extends well offshore. So it may simply be that the 3 moorings from the Pioneer Array have missed the summer jet.
Yeah, that is super possible.
So that's one comment. The other comment is, and having done this before, I think some of the results would be impacted significantly if you eliminated times when warm core rings are anywhere nearby. Since they are 100 centimeter per second feature as compared to a 20 centimeter per second feature. So that big blip that was that Malcolm was focused on almost certainly is a warm core ring, and so are a number of the other bumps. So it's a pain in the neck to go through and decide what is and what isn't a warm core ring. But I think that might impact the numbers rather substantially, and I think your correlations would go up if you got rid of the rings.
Yeah, so we thought about doing that, but then the question is, we have rings. So sure, we are going to find very higher correlations when we do not have it. But if we are looking at a long time series and we actually want to see the main process, right? We will have rings interrupting, and right. So that was why we decided in the end to not go for it. But maybe.
Well, the issue is trying to separate the processes.
Yeah.
So.
Do rings show up in coastal sea level fluctuations, or
I don't think so.
we don't know?
Yeah, we don't.
But,
Yeah.
Yeah.
we'll do that, and then a question from Jack online, and then we should probably stop. So we'll do Daniel first.
Yeah, that's not really my area, but I'm wondering, after studying the SBJ so long, what would be your take on how does it develop in the future with climate change? Thinking the reason you is that AMOC will change in the greater picture, in the next 50 years, would you say this jet increases, decreases with the the overall circulation pattern in the Atlantic, how we think it will develop? Can you tell us something about that? Maybe not, but I'm just curious.
Yeah, I haven't looked so much into the long-term behavior of the jet. I would imagine that it might get stronger as we have more water, stronger water coming from the Labrador Sea until we don't anymore. I don't
It's
know.
almost like a positive feedback loop then,
Yeah,
in terms of sea level rise.
yeah.
Well, I don't want to put that in your mouth. I'm not in the field, but I just wanted to get a feeling.
Okay, so Jack McSweeney asks, in the wavelet analysis, the modulation of the coherence in the 20 to 40-day band, can you discuss further analysis you are doing to tease apart what might be modulating that?
I can discuss. I'm not doing anything.
Okay.
Yeah, that was one thing I was like, wow, we definitely have that, and yeah, I'm not sure exactly how to break it apart. So if Jackie has ideas, I would very much like to discuss it with her. Yeah.
It would be interesting to look at the fluctuations in sea level from the Gulf Stream variations.
We've done that.
Well,
Christopher has done that.
He says he doesn't think it affects the sea level of the coast, but if you're looking for what is the forcing of these, you've shown a very nice correlation between coastal sea level and Shelfbreak jet, but they may be both responding to another force, whether it's like wind scale patterns
Yeah.
or shelf waves
Yeah.
or fluctuations in the Gulf Stream. I'm just wondering, Gulf Stream's 10 times the speed of your jet, but it's further offshore.
Yeah.
So,
Okay, excellent discussion to have over lunch.
all right, I'll shut up.
Anyway, thanks for everyone on Zoom.